the biotransformation of per- and polyfluoroalkyl sulfonamides. Let's start from the beginning. Per- and polyfluoroalkyl substances, or PFAS, are a class of anthropogenic chemicals first developed in the 1940s. They are prepared by two methods: electrochemical fluorination, or ECF, and fluorotelomerization, FT. ECF is a technology in which an organic compound undergoes electrolysis in anhydrous hydrogen fluoride, leading to the replacement of all the hydrogen atoms by fluorine atoms on the alkyl chain. FT is a technology in which perfluoroalkyl iodide is reacted with tetrafluoroethylene to yield a mixture of polyfluoroalkyl chains. These synthesis techniques give PFAS a highly fluorinated carbon chain, which contains carbon and fluorine superbonds. The CF bond gives PFAS unique chemical properties, such as high resistance to heat, oil and water repellency, and surfactant abilities. That is why PFAS are used in, well, everything. PFAS can be found in fast food wrappings, nonstick cookware, cosmetics, and another major use of PFAS are in aqueous film-forming foams, or AFFF. AFFF are used to fight Class B hydrocarbon fuel fires and contain a mixture of ECF and FT-based PFAS. These PFAS can transport from the site of the accident into nearby waterways, contaminating surface water and groundwater sources. There are many kinds of PFAS found in AFFF, but today I will be discussing per- and polyfluoroalkyl sulfonamides, which are PFAS that contain a sulfonyl group attached to an amine. PFSAs formed by ECF technology have a fully fluorinated alkyl chain attached to a sulfonyl group and an amine. PFSAs formed by FT technology have a partially fluorinated alkyl chain connected to a sulfonyl and an amine. PFSA can be further classified by the number of alkyl substituents on the nitrogen atom into primary, secondary, or tertiary sulfonamides. Primary sulfonamides have two hydrogen atoms connected to the nitrogen atom. Secondary sulfonamides have one hydrogen bond and one alkyl substituent, and tertiary sulfonamides have two alkyl substituents. So let's try to make sense of all this. Per- and polyfluoroalkyl substances include sulfonamide-derived compounds called PFSAs. PFSA can be further divided into primary, secondary, or tertiary depending on the number of substituents on the nitrogen atom. PFSA are found in AFFF. AFFF can be further divided into ECF or FT-based foams. The dominant PFSA found in ECF-based foams are perfluorooctane sulfonamidoamine, PFOS-AAM, and perfluorooctane sulfonamidoaminocarboxylate, PFOS-AAMA, which are secondary and tertiary sulfonamides respectively. The dominant PFSA in FT-based foams are 6,2-fluorotelomere sulfonamidobetaine and 6,2-fluorotelomere sulfonamidoamine, which are both secondary sulfonamides. I will be describing the degradation of 6,2-FTSAB, an FT-based secondary sulfonamide, and PFOS-AMAA, an ECF-based tertiary sulfonamide. So, the degradation of 6,2-FTSAB, a secondary sulfonamide, first occurs through oxidative N-dealkylation, which removes its alkyl substituent to form 6,2-fluorotelomere sulfonamide, a primary sulfonamide. 6,2-FTSA is then deaminated, desulfonated, and oxidized to form 6,2-fluorotelomere alcohol, which is then oxidized further into 6,2-fluorotelomere carboxylic acid. 6,2-FTCA can undergo a series of different transformations to form a suite of carboxylic acids with different chain lengths, such as PFBA, a 4-carbon carboxylic acid, PFPAA, a 5-carbon carboxylic acid, and PFHXA, a 6-carbon carboxylic acid. In contrast, PFOS-AMA is a tertiary sulfonamide with a stable terminal quaternary ammonium substituent, The degradation begins here with successive dealkylations of the quaternary ammonium to form a primary ammonium. The primary amine can then be dealkylated and oxidized to form a carboxylic acid substituent. Once both N-alkyl substituents are carboxylic acids, they can be removed via decarboxylation and dealkylation to form PFSa, a primary sulfonamide. PFSa is then deaminated and oxidized to form PFOS, a perfluoroalkyl sulfonic acid. So, to compare FT-based and ESF-based PFSa, the degradation of FT-based PFSa yields carboxylic acid end products. This is due to the carbon-hydrogen bonds adjacent to the sulfonyl group. These weaker bonds allow desulfonation occur, which can yield a carboxylic acid. In contrast, ECF-based PFSa have sulfonic acid-based terminal end products. This is due to the strong carbon-fluorine atoms adjacent to the sulfonyl group, which prevent desulfonation. This leads to terminal end products being sulfonic acids. To compare primary versus secondary versus tertiary sulfonamides, evidence shows that the stability of the N-alkyl substituents has a large impact on the rate of degradation of PFSa. For example, the quaternary ammonium group on the secondary sulfonamide requires several N-dealkylation steps to degrade, and is slow to do so owing to the stability of this terminal end group. In contrast, a tertiary amine with relatively simpler substituents, such as a carboxylic acid that can be transformed via beta oxidation, can readily degrade due to the simple nature of its substituents. While the degree of amination can produce steric effects that hinder biodegradation, the nature of the end substituents exerts a greater effect. In conclusion, FT-based PFSa form carboxylic acid products, while ECF-based PFSa form sulfonic acid-based products, which are more toxic and persistent than their parent compounds. In addition, the degree of amination of PFSa has less of an impact on the degradation of these compounds than the complexity and the stability of their N-alkyl substituents. So, while there are differences between FT-based and ECF-based, and primary versus secondary versus tertiary PFSa, in general, the mechanisms behind the transformations need to be further studied. In addition, the incomplete degradation of PFSa can result in more toxic end products such as PFOS and PFOA, so biotransformation efforts of PFSa have been unsuccessful thus far.